Hello, it's Dave Giles here for the first lesson of Cambridge International Education IGCSE Physics. We're looking at the electricity and magnetism unit, focusing on electricity now. And just to start us off, we're going to look at the static electricity. So put a little starter question on here of naming three places you may encounter static electricity. Some of the ones I came up were a lightning strike, dusters that attract dust. So when you are dusting your house or when your parents are, and they might have a long duster, it actually attracts the dust. It's not just sweeping it off, it's actually attracting the dust, some of them. Crackles when combing your hair, cling film sticking to your hands, dust being attracted to television screens. If you've walked up to a TV screen that hasn't been dust last couple of days, run your finger down it and you see all the dust. Clothes clinging to each other in a dryer, getting a shock after rubbing your feet on a carpet and then touching a metal object. Okay, so there's some places you might find static electricity. So today, like I say, we're looking at static electricity and electric fields. And I want you to state static electricity is stationary electricity. Describe how static electricity is generated. We're going to look at a Van de Graaff generator and a gold leaf electroscope, look at how they work, and describe the field around a point charge. So static electricity is due to the build of electric charge. It's called static electricity because the charge is unable to flow. The build of electric charge can cause dangerous sparks, which is obviously not something we want. Sometimes after walking on a carpet, then touching a metal object such as a doorknob, you might get a small shock. This is caused by static electricity. And sometimes if you're going up a escalator, you might find that as well. So, a quick question. Describe the difference between electricity in a circuit and static electricity. Now, we haven't looked at circuit electricity yet, but you should have some knowledge of that from Key Stage 3. And give you a few seconds. The answer is that electricity, or the correct term is current, in a circuit flows. Static electricity is stationary, so static electricity can't move from one place until you discharge it. And we'll look at this in a little bit more detail during the course of the lesson. So, static electricity is due to electric charge that builds up on the surface of an insulator, such as a plastic cone. Pardon me. The charge that is built up cannot easily flow away from the insulator, which is why it's called static, because it can't go anywhere. It's stationary. Static charge can build up when two insulating materials are rubbed together, such as a plastic cone moving through hair. Friction between the materials causes electrons to be transferred from one material to another material. So one material ends up with more electrons. So electrons have a negative charge. Okay, so if you're going to have lots of electrons, then you're going to have an overall negative charge. The other material loses electrons. Now, normally something is neutral, which means it's got the same number of positive charge from protons and electrons. So if you lose some of the negative charge, you're left with more positive. So you end up with an overall positive charge here. So a little demonstration. So you rub a cloth on a rod here. You can see now, in reality, you're going to have lots more than two electrons and two protons, but it's just a simplified version of it. So you can see here the rod loses electrons to the cloth. So the rod has got a charge of +3. The cloth has now got a charge of, you've got 5 negatives, 2 positives, so it's -3 overall. This rod, on the other hand, this time the electrons move from the rod, say from the cloth to the rod. So you've now got a +2 charge on the cloth and a -2 charge on the rod. Friction causes negative charge electrons to be transferred from one material to another, is what you need to know. So quick one-word answer questions. So which force causes static charge? The answer is friction. Which particle is transferred to or from an object when static electricity builds up? That is electrons. And on what type of surface is static charge typically built up? That is insulators. So let's have a look at some MCQ questions now. you rub a balloon on your hair. The balloon becomes positively charged, therefore your hair, well, the only thing that is transferred is electrons. However, if your hair becomes positively charged, then you have gained, you rub a balloon on your hair, the balloon becomes positively charged, so electrons have moved away from from the balloon to your hair, making it negatively charged. You're walking on a rug and gain positive charge. When you touch a neutral doorknob, well, let's go through the options. We'll start at the bottom. Protons flow from your hand to the doorknob. Well, protons don't flow. Protons are much, much bigger than electrons, so they don't flow. So I'm going to rule out D and C because they both talk about protons flowing. Electrons flow from your hand to the doorknob and you get a shock. So when you're walking on a rug and gain a positive charge, well, if you've gained a positive charge, you can't have electrons flowing from you because you've lost charge already. So it's going to be electrons flowing to you. So they flow from the doorknob to your hand, giving you a shock. A polythene rod repels an inflated balloon hanging from a nylon thread. Why do the rod and the balloon repel? So the rod and the balloon have opposite charges. No, opposites attract. The rod and the balloon have like charges. Yes, it's that. And question 4, which will make the last one. Diagram 1 shows two thin, uncharged strips of plastic. Diagram 2 shows the same strips after they have been rubbed with a dry cloth. Which row describes the charge on the strips after rubbing and the force between the strips? So charges, um, you can see that, well, the force between the strips, they are repelling each other after. So therefore it is B or D. So in order to get repulsion, you need to have the same charge. So therefore the answer is D. Okay, so that's describing how static electricity is generated. And this is kind of also about static electricity, but it's two specific examples. We're going to look at the Van der Graaff and a gold leaf electroscope. So a gold leaf electroscope can be used to detect charge. The electroscope consists of an earth metal case inside which a metal rod is connected to a metal plate. A piece of gold leaf is attached to the other end of the metal rod. So you've got this gold leaf here. When the metal plate becomes charged, the charge spreads out through the metal rod and the gold leaf. The metal rod and the gold leaf gain the same charge so that the thin gold leaf is repelled from the rod and sticks out. So normally if it's uncharged, then this will lie flat. Once it becomes charged, you've got, say, a negative charge here, you've got negative charge there, you've got two opposite, so say two like charges, which will repel each other, causing deflection. And the more charged it is, the more it'll deflect, so the more it will go up here, which can be measured also using this scale here. And the other one is a Van der Graaff generator. So let's have a look at how they work. So the Van der Graaff generator contains a rubber belt. As this moves, friction generates charge. The charge collects in the metal dome on the top of the Van der Graaff generator. So you've got a lot of charge collecting in here. Now it's actually positive charge, so it's losing electrons in the dome. When an object connects to the Earth, now charge wants to flow to Earth, and we'll talk a little bit more about that later. As brought near the dome, the movement of charge between the objects and the dome causes a spark, like you can see there. Now, if an insulated person, now insulated basically means you're not connected to Earth. Now, charge wants to flow to Earth. It wants to, the word is dissipate, it wants to spread out. So you've got, say, a load of negative charge, keep it simpler, a load of electrons. They want to move away from each other. They want to repel each other. So they want to spread out, what's basically go to Earth. So however, this person's not, so he stood on, say, a plastic chair, for example. So it causes, when he puts his hand on it, his hair starts to stand up. And here's an example of me with a Van de Graaff generator. So this is me in a classroom of an old school I worked in. And what I've got here is I've got a Van de Graaff. And now this second, the big dome here, the small dome is connected directly to Earth. So at the moment, I've got some pie tins on the top here. Now, they're just basically thin sheets of tin foil, or aluminium foil rather, that are on top of there. And I turn the Van de Graaff on. Initially, nothing happens. Then I move this second dome away. Sorry, it's not, it's paper I've got in there, sorry. I move the second dome away, which is connected to Earth. And now, instead of the charge flowing to Earth, the charge instead is now built up on here. So these pieces of paper have all got the same positive charge. So they all repel each other and they fly away. I'll go back again so you can see it. But it didn't happen at first because initially it was Earth. And you also, if you look in the background, my whiteboard, my projector rather, the electric field actually is quite strong and it interferes with the projector in the background. You can see it going off. That usually happens when we get a big spark, so there must have been a spark there which I couldn't quite see. So let's have a look at what happened. So initially the small dome is touching the large dome, earthing it. When it is moved away, the large dome becomes positively charged due to removal of negatively charged electrons. The paper also becomes positively charged. Like charges repel, the paper all flies away as the paper is repelling each other. And another common experiment, and I showed you in that little video earlier, is you get a student, they'll stand on on an insulated material, say a plastic or wooden chair. They put their hands on it and the hair sticks up. But why? So, very good question. I'll give you a moment to have a go at it. So, this is not a past paper question, but the first one would be very simple. It might be worth 1 mark. The second part of the question, so describe basically means what happened. Explain why it happens. Okay. So the second one would probably worth maybe 3 or 4 marks, something like that. So, what happened when she held the Van de Graaff generator? Her hair stood up or spread out. So just describing what you see. Explain why. Positive charge built up on her hair. Like charges repel. As all of her hair is positively charged, each individual hair is repelled from each other, causing her hairs to spread out. Okay, so that's the third learning objective. Apply knowledge of static to a Van de Graaff generator. Complete. So we'll have a look at, actually 2 seconds, just going to pause this. 2 seconds. Okay, so this is a past paper question from the UK curriculum here. It's 3 marks, and personally I think it's a bit of a generous 3 marks, but it is a 3 mark question. So Van de Graaff generator is used to investigate static electricity. Pardon me, before it's switched on, the metal dome has no net charge, so the overall charge is 0. After it is switched on, the metal dome becomes positively charged. Explain how an uncharged object may become positively charged. Okay, let you pause it, give it a go. And the answer is negatively charged. So you get 1 mark for that. Electrons are transferred. Now, the first bit might actually seem a little bit obvious because you might just say electrons are transferred and forget to mention the fact they are negative, but you do get a mark for mentioning they are negative. So negatively charged electrons are transferred from the object or from the neutral object. And that's 3 marks there. I would say it's quite a generous 3 marks. But anyway, moving on. Our next learning object is about describing the field around a point charge. So around electric charge, there is an electric field, just like a gravitational field around a mass. So if you look at space around a field, so this here is an electric field, you can see we always draw it going from positive to negative. So if we've got positive charge, we draw it going outwards, and if we've got inward charge, so if we've got negative charge, we draw it going inwards. And the reason this we use this convention is we're looking at which way a charge will move, a positive charge, sorry, will move if we place it in the field. So the electric field lines are drawn to tell us which direction a positive charge would move if it were placed inside the field. Since the source charge produced in the field is negative, a positive, in this example, a positive charge would be attracted by a force towards it. So the force on a charged particle decreases with distance from the other charged particles. It's an inverse square law, but you don't need to know about that. So as you get further away, the force becomes weaker, or alternatively, as you get closer, the force becomes stronger. And the way we can see that is if we look at an electric field here, so this is going from positive to negative. If the lines are closer together, then we've got a stronger field. Similarly here, if we have a point charge, and now if it's going away, will that be positive or negative? Quick question. So it's a positive charge. It'll be repelled if we put a positive charge inside the field. You can see, obviously, this one here is a stronger field than this one because the lines are closer together. But if we look at this one, you can also see that if we are close to the charge, the lines are close together. But as we move further away, the lines become further apart, so it becomes weaker and weaker as you move away. So the greater the bill of charge on the domes, the greater the electric field. Eventually, the electric field is strong enough to create the force on the electrons on the dome to rip them away and move them towards a positive dome. So a Van de Graaff generator is charged positively. Initially, there is no spark to the earth or neutral dome. As the dome is moved closer, a spark is observed. Why? Well, the nearer the grounded dome comes to the positive charge dome, the greater the force applied to the electrons. Eventually, the force will be great enough to pull the electrons across the gap. Okay, and we'll end with some paper 2 multiple choice questions. Which diagram shows the electric field between two oppositely charged parallel metal plates? So it's going to be straight lines. So we can rule out C and D straight away. And we say the lines go from positive to negative, so it is A. Which statement describes the direction of electric field at a point? So let's go through it. The direction of the force on a negative charge? No. The direction of the force on a north pole? It's not related to magnetism, so no. So that also rules out D. So the answer must be C, the direction of force on a positive charge, which is what we said earlier. So the answer is C. Which diagram shows the electric field pattern and direction around a positive point charge? So if it's positive, it's going away, and it's a straight line. Sorry, it's not a circle. So the answer is therefore A. Okay. The last question, the diagram shows points between X. So again, the diagram shows point X between two charged plates. Which diagram shows the electric field pattern near the point X? Okay, so it's going to be straight lines. So I'm going to rule out C and D. And it goes from positive to negative. So positive and negative here would be A. Okay. That's it for today. The next lesson, which I'll be uploading soon, is on circuits and charge. Thank you very much, everyone, and I will see you later.